Okay, I think we can get started, and even if you have not finished, we'll just walk through it together. Okay, so first, what we would like to do, and please, guys, feel free to jump in at any time if you have an addition, if you have a question, and so forth. So what we would like to start with is for anybody who joined us today and who wasn't with us on Wednesday, let's just describe the problem and what this chapter is doing. Let me zoom out. Okay. Okay, and this should be a good size for everyone to follow with me. If you think I should zoom in or zoom out, just tell me. So this chapter 2, what here what we're doing is, and I'm just gonna read here. So we have this data set that was given to us. It's an old data set. It's in from the 1990, but it's fine. It does a good job on describing a problem that we would like to model and to end using a machine learning algorithm. For instance, here, what we're doing, we're predicting the housing prices at specific district in the California state. So that's what we're going after. How are we predicting this housing prices? We have this data set, and this data set, so it's a tabular data set, and this tabular data set has features, and from those features, one of the columns, and oh yeah, okay. So this is what I'm talking about. So this is, by the way, so this is what we did last time. So we just loaded the data. We talked how you want to maybe set up your Jupyter notebook within an environment with the libraries installed within that specific environment, and a few other things. So yeah, so the data set looks like this. So these are the different features, and one of them is the median house value. So that's what we're trying to predict. Okay, so we're gonna use the rest of the features to predict this median house value. Actually, yeah, it's nice maybe to walk through the notebook really quick because it was short, but we had a good discussion last time. So after we load the data, the first thing that we would like to do is examine the data, right? Well, and really what we talked about even before, a key point to even before working with the data is to communicate with your boss or with the team with the overall picture, right? Because usually the machine, like we, maybe machine learning engineers, we think that the machine learning model is all, right? But really it's just a part of the big picture. So it's very important to align ourselves with the big picture. What's the end goal? And usually, for example, for companies, usually it's a product or it's a service and so forth. So yeah, so the first thing is good communication with the team, with whoever you're working with, and then you load the data, you work with the data, you do some EDA and so forth. I think we'll get to this. Okay, so we went through all this, and okay, and we had a good discussion about histograms. If I would like to maybe recap on anything that we said, we did talk quite a bit about outliers. What would you consider as an outlier, and maybe not necessarily an outlier? And I would say good references are on Slack channel, on the chat. And I think statistically speaking, what was shared, the 1.5 is a good way. 1.5 of the quartile between usually between like 25% and the 75%. If that quartile is 1.5 of that, 1.5 of that added to the 75%. If a point fails like outside above that, then we can consider that as an outlier. But anyway, that's on the chat. You can go to the chat for that. So today, so with that, before we start today, I'll pause and maybe take any questions up to this point. Okay, cool. Okay, so we are creating a test set now. And he says here it may be strange to voluntarily set aside.
Salim, this is Shubhashish here.
Yeah.
Yeah, just one question regarding what we covered on the other day.
Yes.
So they talk about k order norm, right? Here we are talking about second norm, L2 norm, and L1 norm. But in the same go, they're also talking about k order norm. So any idea where higher order norms are used for any purpose? So the L2 norm is the RMSE, and the L1 norm is the MSE.
Right.
So any other higher order performance metrics which uses higher order L norms? Any idea on that?
I mean, as far as I know, so we talked about them. We talked about them for the performance metric, right? So, like for example, even the zero norm, it's used for other measurements as a performance measurement. I'm not aware that we ever use above, but somebody can jump in on that if anybody want to add to that. Do we ever use anything other than those two? I have not. Is anybody more familiar with this?
I haven't seen any instances of that, but I can understand why they might want to use it in a case where they're very sensitive to outliers, and so the higher k is, the more you're stressing on the more the outliers dominate the result, right? So you know, if you have L2 norm, then then the errors are squared so that in the calculation of the norm, so a few very deviant points can skew the error and make it very large. Well, you can imagine that if you go to higher order norm, like a L5 norm or whatever, or a L10 norm, then the errors, the large outliers, are going to dominate the error even more, and that's the situation where you might use it. I have never seen it used that way, though.
Right.
Yeah,
so I was just wondering if there is a provision of k order norms, so where they might think of using it. Anyway, so yes, I understand that for our cases we don't use that because that is very much vulnerable to the outliers.
Yeah, I guess it's just a measure of how sensitive you want your model to be to the outliers. Maybe there are certain specific domains where even like a small shift in, like if you have even just one or two outliers and you want to know about them and maybe drop them from your training or something, that's when you start using higher K.
Yes, maybe one situation. Okay, thanks. Not an issue. Okay, let's go ahead.
Yeah, so like I said, I haven't personally used more, but again, as we said, it's L2 norm would be more sensitive to outliers than and same thing for higher order norms. Okay, so create a test set. So here, yeah, so here we're splitting the test set. But he's saying we're splitting the test set as early as we are in this experiment, but that's very important. Why? Because we actually want to split the test set before we look at the data. Okay, because what happens, and that's automatic, once we look at the data, we may start making some assumptions, and which will lead on actually bias in selecting the test set. So, and this is where it's called data snooping bias. So we definitely don't want to. So we just want to split out the test set as is. Okay. Okay. So how do we do this? So usually, of course, we are familiar usually with the 80%, 20. So, and again, here we're only talking about, later on, maybe we'll get to talk about, you'll often hear that there is a training set, there is a validation set, and there is a test set. Okay. For now, we're just thinking that, hey, there is just a training set and there is a test set. Okay. The training set is, for instance, here is 80%, and the test set is 20%. So here he uses a function that he did, which is very similar to the scikit-learn split function. And so what we can do, okay, so that's he has that. Okay, and any questions here what he's doing? So pretty much, and I'm not sure how much in depth do we want to go about the code. I mean, if you do have any questions, please ask me if about any specific function that he used. But I feel maybe we can just keep going so we can cover more.
Yeah, so I had a question here
Yeah.
on the train and test split.
Yeah.
When we're doing it just by raw percentage, and suppose we have, for example, well, I'm thinking in cases of like, well, I guess I'm thinking in categorical, not regression.
Okay.
Maybe not this example, but I'm thinking if you have or splitting your train and valid, and you have a number of classes, and you want to make sure that the classes are equally represented between the train and valid, like suppose if you do a percentage and some classes do not appear in either the train or the valid, then that would be
right. You don't want that because
yeah.
there will be like an imbalance. So okay. So here's the thing. If you assuming that you have a balanced data set, assume that you have a balanced data set when you do a test, when you do a split, it should be fine. So when it's balanced, but usually when it's an imbalanced data set, that's definitely something that you want to deal with. Yeah. So yeah, so there's something at the beginning that you would want to know: is your data set, is it a balanced data set? But again, here we're doing regression, and I feel you're talking about classification. So maybe
if you use scikit-learn's train test split, there's a parameter for stratify that will allow you to do that stratification.
Exactly.
So stratification is the one that achieves that equal representation of classes in both.
I believe so.
Okay. Thanks
for that. Okay, so here we did the test ratio, so it's the 20%, and okay. So here is so there were a few questions about hashing. So before that, one solution is to save the test set on the first run. Okay, what are we here? Let's see here. What are we talking about? This works. Well, this works, but this is not perfect. If you run the program again, it will generate a different test set. This is actually very, very important in all machine learning algorithms. For us to be able to compare always our runs, we always wanna set a seed, right? So that way, that seed makes sure that the sequence of random generations following to that are the same. So that way we can compare the results between this run and then when we change stuff and then the following run, right? And this is his first suggestion. So we want to specify a seed. And the other suggestion that he says, oh yeah, you can save the test set and then you can load it every time. But again, both these two, they have the limitation. What if your data set just grows, right? What if your data set then grows? Both these two, they will. Why would they fail? Because what happens is, let's say what happens is, okay, you've selected 20%. You had 1,000 samples, and you selected 20%. So that's like 200, but then you added another 1,000, so now you have 2,000. But then, okay, you will select 400, but the 400 may not include all the 200 that they were there in the first place. But what we want to do, we want to still have the 200, okay, and then we want the new added 200 to come from the new added data sets. Okay, I hope that's clear. And that's why here he's saying use a hash function. Why if you use a hash function? Because even if you add more data, okay, when you hash something, well, let's say for example, when you hash, you have an identifier, an ID that you hash, the results of the hash function will not change even if you add data. So it's fine, okay? And this is, so that's the solution that he has, and this is what he has implemented here. And so here, briefly, what he uses the CRC32, which is just a hash algorithm, like many others, like MD5, I believe, on his notebook. Let's go to that part. Yeah, so you see how here, for example, he also suggested an MD5. So all these are just different hash algorithms, the way how they do the hashing. For instance, here what this one is doing, the CRC32, it takes an identifier and it hashes it into 32 bits. Okay. It hashes it into 32 bits. Okay, so that's the result of this one. And actually, you know what? And when I was talking, I know this is like still the beginning, so I'm assuming maybe some are new to this. So with that, and this is why it's nice to have the notebook running at the same time. So for example, let's go to this one and just share this. So for example, okay, so looks like I didn't even run it. Okay, good. So now I run it here. So what I'm trying to show is, okay, so this one is going to give you like a 32-bit value, that this is just a mask, that you just mask it with this one, and then you say, and again, you see it's the same size. So I said this is 32. This would also give you, that's what you have here, to the power of 32. And if it is smaller than a specific value, so what it is, okay. And so we're here. So this is a function of the test set check. This is a function that he has for the split train, okay? So what he does here is, he calls them both here. You can see that this one calls really this, and within this one, he calls our hash function here. Okay. Okay. I hope this is clear. Please ask if you have any questions about this. So here, for example, what he has, the first thing that he needs an identifier. Where can he find an identifier? Okay, he said, let's just create, yeah, I believe, so he created a new column. He added a new column by resetting the index here. So here we have a new column called index, okay? And then that's the, so do you see, so that's our column index. So that's our column here. You see how here we have this column index here. You know what, let me see if this, oh, okay, great. I think I have this tool. Okay, that's the column that was created. That was not there before, so he created that. And okay, so yeah, so he fed that into this one. And by the way, so here lambda in Python is just a function. So what he's doing, he's applying this function here. He's applying this function here, that function, to these IDs. And what are these IDs? It's just this column. Okay, and then here what he says is, what happens is when he does data.log that and that, what happens is this one gives him true or false. So the true ones would be the test, and that's how he gets this one. And then the false ones would be the train ones, and that's how he got that. You know what? And we can, okay, yeah. If I would gladly, maybe we can actually debug and see this one, what I'm talking about, if anybody have any questions. If not, that's fine. Is that clear? Because this is actually, this is a key point. This is a key point. Okay, well, what he's saying also here, that you see how we use this index as an identifier, okay? Sometimes we can use two features to make an identifier. So for example, he chose here longitude and latitude. What's really important about this identifier is it has to be unique, okay? It has to be unique. And for example, it can change. For example, when you add the data, for example, let's say you have this row that has this specific identifier. When you add your data, you do not want that identifier to change. And here, for example, and that's how, for example, when he uses two features from that specific row, for example, here longitude and latitude, even if he adds data, the results would just be the same. So you can use that too, okay? That's the thing. Here, for example, when we add data, we have to make sure that we're appending the data. So the new data would have the new appended indexes, so they're not mixed up with the top ones. Okay, I think that's good. If any questions about this, so for example, when I was just running this one, I went, okay, I said, okay, let me see what am I getting with this one. So for example, here, what we can do is, so for example, we can, you know, so for example, here we can give it an identifier. Okay, so for example, let's say this 59. 59, what's 59? It's going to be like, okay, it gave us false. It gave us false because it's checking if this one is less. But if I would like to just do this one, I can just, and then here I can do my 59, and that's the value. So that's the value that it's getting. So, and again, this will always have this value using this specific hash algorithm, okay? Even if you add that. So I believe that is clear. If any questions about this, please ask now. Otherwise, we're gonna move forward. Okay.
Just to summarize then, the hashing allows you to, it gives you a mechanism so that you can create data sets that that will always be the same, no matter if you add data and so on. Those data will get sorted into training and validation set in a repeatable way, so that at the end of the day, when you have all your data together, at every stage, you know, you can ask for what is the training and test set, and then after you incorporate new data, it's repeatable. You can always retrieve that, which is a better idea than just saving the data sets or something like that, like he was talking about before. So we're thinking in terms of a model that is continuous or at intervals taking in new data, and this is a mechanism to make sure that it's repeatably assigning the data into training and test sets.
Thank you, Joseph. Okay. Okay, I believe that's very clear.
I have a quick question.
Yeah.
Does anyone know if scikit-learn has that built in, or?
Oh, like a built-in that you can just. I haven't, but I mean it's just as straightforward as he has it here. I have maybe if maybe there is, I have not used it through scikit-learn. Usually you can just call some hash algorithm through something like this and then do it like that. Yeah.
All right, thank you.
Yeah. Okay. Okay. So.
So excuse me. The new version, I just looked this up. The new version of scikit-learn, version 0.23, has a method called feature hasher. So you can do the hashing with scikit-learn now.
Oh, awesome. Okay.
Thanks.
Okay. Well, okay, so somebody will, okay. Maybe, okay, cool. So there is this one. Okay. We'll read up on it on that later. So as we talked before, this is what we're doing. So right now, actually, even for going back to actually one of the fellows, he asked that question of for the classification for the classes, but I think it's also applies a little bit for here too. So how do we really select the samples? So right now we're just doing random sampling, right? And stratified sampling was proposed, which is very much recommended when, like for example, imbalanced data sets. So for example, let's see the example that here that he gives. So we have considered random sampling methods. But for example, let's say this is fine if our data set is large enough. But if it's not, you run the risk of introducing a significant sampling bias. For example, he gives the example where a company decides to call 1,000 people to ask them a few questions, and they just cannot pick 1,000 people randomly. They have to ensure that the 1,000 people are representative of the whole population. And for instance, if the population has 51.3% females and 48.7% males, we definitely want to take that into consideration. And this is where he suggested stratified sampling. And okay, and he gives here a very good example. So what's stratified? So stratified sampling pretty much is you just try to group what you have into groups, into strata. So a strata is just a group. So you try to group your data set into different groups, and then you sample from those specifics from those groups about the same. Actually, you would like to, for example, let's say on average about the same from each group. So that way you have a good representation of the overall data set. That's what stratified sampling here. Here, for instance, he follows that with the example. Okay, he says, okay, called strata. Okay, that's the definition. If the people running the survey used random sampling, there would be about 12% chance of sampling a skewed test set, which is significantly biased, right? That was either less than 49% female and more than 54% female. Okay. Right, while the US population of female here is 51.3, right? So for instance, and by the way, how did he get, so I believe there was questions on how did he get the 12%. I can explain that if somebody else already looked into that and would like to go ahead and talk about how he got the 12%. Please feel free. Anybody want to say something here? Okay, so so how did he find out? So this is maybe for the statistics fellows who are with us, maybe they can. So this one, so what he assumes, so this is like a binomial distribution, and because it's large enough, you can consider it as a Gaussian distribution. So the mean and the variance. So the mean would just be NP. The mean would just be N, which is our N, which would be 1,000, right? P, our probability for females is 51.3. So our mean, for instance, let's say is 512. Our variance would be for this distribution NP times 1 minus P. So actually, you know what? I also saw a nice blog about it. So instead of just saying all that, Actually, I have something that I can just share on the chat. Let's see. Yeah, I believe it's this one. 1 second. So yeah, so anyway, so you get that. Oh yeah, perfect. So somebody was reading the book and they asked their specific questions, and I believe one of the fellows asked that last time, and that's why I'm answering this now. So yeah, so you get the mean and you get the variance, and from that, okay, you have your standard deviation. Okay, from the standard deviation, you can get the z-scores. Okay, so we're looking for z-scores. Again, here what we're here what I'm covering here, where does the 12% of sampling came from? If we do it randomly, right? Okay, so once we have our standard deviation, then we say how much. So for example, so for instance, here we do 5. So we do, for example, so here the first one. So we do 540 minus 540 minus 513. That's 27. 27 over our standard deviation would give us 1.7. And if we do that, and so I'm bringing my calculator. Okay, doesn't want to go to that screen because it's okay, it's full. But yeah, so if we do 27 over 15.8, that's going to give us 1.7. And same thing, if we take here the 490 minus 513, let's say that's going to give us what, 23 over 415.8 will give us the 1.45. And again, here what he's saying, to get the probability of them being outside is same thing as 1 minus probability of them being inside. What's them of being inside? We go and we check the z-score table, and if you go check the z-score table, so we're actually to the right of this one, we will find this value, and for the positive and for the negative, we will find this, and that's how we get the 12. Okay, so that's okay. That's on the chat. Let me.
I was making a drawing here that sort of illustrates what's going on. So
yeah,
if this is the Gaussian distribution. This is minus 1.45 out to here, and plus 1.7 out to here. And so what we're doing basically is we're integrating the area under the curve of the Gaussian distribution outside of these limits. So this is the this is the minus 1.45. Sorry about this horrible writing. And this is the 1.7. So what we want is the probability that the sample is outside of these limits, and it's basically the integral. And so what this phi is basically the integral of the Gaussian distribution out to a certain number. So phi of 1.7 is the integral of the Gaussian distribution out to 1.7. The whole integral of the Gaussian distribution is 1. So if we want to find these two pieces, we want to subtract we want to subtract 1. We want to take 1 minus phi of 1.7 minus phi of minus 1.45. Phi of 1.7 is this piece, and phi of minus 1.45 is the piece on the left. So that's the logic there. He's saying to get the area outside the curve, you take the whole integral, which is 1, and you subtract from it this piece, and that gives you the other. So that's that.
Thank you, Joseph. Okay, I believe that's clear. Okay, thanks. Okay, so
quick question on stratification.
Yeah.
So the example that I was thinking of and that I'm kind of familiar with is on the deep learning side of it. When you have certain imbalance in classes, like you were mentioning, you do stratification based on the classes, which is kind of your Y value, right? The value that your target. But the example here that is being mentioned, you're doing stratification based on one of the input features. That is, am I missing something there, or is that kind of common? That's the first question. And the second one, follow up to that is, what if you have like this category would be called like sex, male or female. You could have another category which probably would be like country. You could have an imbalance in country too. You could have like many more which could have imbalances. So is there a certain way like you would stratify based on one column, or would you do like something like a branching, stratify on one column followed by the other column? If that question makes sense. So yeah, those are the two things.
Yeah, they definitely make sense. Anybody more familiar with that? Like I haven't used too much of stratification. So anybody wanna? Yeah, I mean, but both questions are so. So the first one, again, to reiterate the question, the first one. The second one was like if you have many that you would like to stratify based on, and the first one was again if this is very common. The first question, I mean, this is very much recommended instead of just randomly sampling the data. Okay, and is it because it's one of the inputs? Yes, definitely, because if one of the inputs, that's fine. Actually having two and doing stratification based on two, that's I'm not familiar with. Anybody?
Sorry, going back to the previous question that you answered, to reiterate, like if you're doing fraud detection, right?
Yeah.
So you have an imbalance in the target. You're going to have a lot of non-fraudulent transactions and a very small percentage of fraudulent transactions. So my understanding was you stratify based on that. But here what the author is saying is you're stratifying whether the fraudulent transaction happened on a man's card or on a woman's card, which is on the input feature side.
Right.
So I'm confused, like, is stratification, which side do you do stratification based on? Is it based on your target feature or based on input feature?
So it looks like that you can do it based on any feature.
Oh, I see. Okay.
You see?
Because the true population is like 49% female and 48.7% male and 51.3% female. So you don't want to have even the training sets with your features that are not representative of the population. So I think that's what it meant. And yeah.
So you do specify just that specific one. So here it does not really matter if it is, let's say, your predictor or it is one of the features. So you can split based on any. The other question, which I think very interesting, what if there are two that you would like? There's that, for example, this one is from scikit-learn. So this is a stratified shuffle split. I don't know if it supports really two. Anybody have played with this before?
Yeah, well, I haven't played with it, but I just looked it up. In the new 0.23 version of scikit-learn, they have a multiple label stratification, and I just put the link on the chat.
Thanks,
so
Joseph.
to Rickle's question, Rickle, is this try out this answer that I'm about to say because it's not fully formed and see whether it makes any sense. pertaining to even the prior person's response. When you know that Y is, or when you stratify based on Y, then you know the Y to X relationship. In other words, if Y is different, then you want those images of that class, you expect them to be different, then you stratify on Y. As the prior person said, when you know that X distribution in your data that in your population is something and your subsetting might not result in the same, then you would subset it such that the distribution is what you would see in the population. So that also answers your other question of, would you do it in a sequence if there are multiple variables? What I believe the answer should be is your final data should represent the distributions that you would see of those variables in your population. To the extent that the data you model with is similar to that, that's your goal that you're aiming to reach. However you reach that is more a how, but that's what you would want to reach. Does that make sense?
Yeah, that makes sense now. So here, the specific part that I was missing was the idea of subsetting. You're trying to hold the stream stratification.
Sorry,
right?
repeat that.
For the important thing is that you're subsetting over here, and the subsetting should be done in such a way that you hold the same stratification as your input data, so that it represents that as much. Okay, now that makes sense. Yeah.
Yes. Yeah, correct.
So the something that is still open for me is like, is that automatic? Like, suppose I have not just the gender, but a bunch of other input features that are imbalanced. And if I were to do the stratified shuffle split, is it clever enough to know that all of these are imbalanced and maintain that same in both the splits? Or do I need to specify it specifically?
That's where I think Joseph's multi-label might come in, and somebody would have to try it to see that if you gave it the labels, multiple of them, then it probably does. But then that's on a label basis, and your question is on the input basis. So
I mean, my question will also hold for the label basis. I'm essentially speaking of either the X or Y that are imbalanced. If I were to simply call this function, will it understand implicitly that it has to maintain the same split for all of the imbalances, both on the X and the Y side?
I think you're passing column names in, right, that you want to hold the split on. If I'm not wrong, that's what the scikit-learn function expects. I could be wrong. Wait, let's look at the code.
Yeah, I tried looking for where we're specifying a column. I didn't see it, at least on this.
So it looks like what Joseph has shared, this is exactly what the question was. So yeah, so if anybody, so if anybody actually does try this one later, please, like within 2 different features, the stratification based on multi-label, please share what you get, or maybe we can try it now, or maybe at the end if we do have time. Okay, so somebody was checking something. Any additions before we move on?
I just have a question, Salim. Have you seen, with regards to stratification at scikit-learn, how you can use time series data or how stratification is impacted by time series data? So to go back to the example between male and female splits. So if that, I think it was 51-49% in the example. So if that changed to 55-45%, for an additional series of time points, can that be accounted for in scikit-learn, or maybe you need a more custom implementation to account for that? But I haven't seen it in scikit-learn, and I'm just wondering if you'd seen it when you were looking through it.
I'm not sure. Yeah, I'm not sure about that. The way how it is implemented here, I mean, again, and again, it's nice at the end, and this is where we're getting to, there is a comparison. He does make a comparison between the stratified results and the random, and using the and he compares that. But yeah, going back to your question, I believe playing with this more, actually, I want to share this before we move on. So this is a nice one that I crossed at scikit-learn, visualizing cross-validation behavior in scikit-learn. So for example, what I'm very familiar with is, of course, and we all probably are, is cross-validation, right? When you do k-fold cross-validation and so forth. And we can relate stratified cross-validation to our k-fold cross-validation. And in this page here, what they do, they give the data class, right? And then they give the data group. And then what they do, they say, okay, for k-fold, this is what happens. So for example, on k-fold, we say, oh, okay, for example, here, what are we doing? Here, we train on all this, and then we test here, and then we train on this, and then we test here, right? And then what's a stratified k-fold? Oh, okay, so a stratified k-fold is we try to go to every class, and then we try to actually apply k-fold on every class. So we go to this class, and then we apply k-fold on this, then we go to this class, and then we apply k-fold on that, and same thing, right? And then they show even others. And it's nice how like they have, okay, and then they go to the shuffle split. So this is what we just seen. And then they go to the shuffle split and the stratified k-fold. So this is something I'm going to share on the chat. I believe this can be very helpful.
And then there was the question about the time series stratification. I don't see a way to do that inside of scikit-learn, but you can do it yourself by making some new making a new category which says, you know, which part, you know, you can say the first 10% of the time series is in category 1, and the second 10% is in category 2, and so on. So you could make your own new columns, and then you could stratify on those. So that's a way you could do it yourself.
Yeah, I was thinking that maybe, yeah, you could group by on the Pandas data frame by day or by week or whatever. And
there is a function for that. There's a time series split. So that will keep appending from the first 10% of your data. You keep increasing. So in the first fold, it will be like only initial 10% of your data is used. The second fold, you would use the first 10%, append another 10% to it. So 20% of them. So you keep aggregating based on your date. It's called, I think, time series split.
Oh, okay.
Okay.
I can share that link if I find it. And like was shared, I think that also has a nice diagram that exactly explains how it does it. I'll share the link when I find it.
Okay.
Okay, thank you.
Can I add one point? I remember when I was reading Jeremy Hauer's note on cross-validation for time series, it just doesn't apply because for time series data, there's seasonality, there's like information with sequence. So like I think we just have to be really careful when we try to shuffle the data in any sort of ways, because we might lose information when it comes to time series.
So you're not shuffling the data there, you're still holding the order of the data. Shuffling is a bad idea for time series. This one, you still go in the same order. So if the dates were arranged 1 to 100,
I'm not saying about this.
Yeah.
I was just saying the other ones. I don't know about like stratify, shuffle, and cross-validation, how these are implemented, and perhaps time series splits is the optimized way to do it.
Okay, so stratification with time series, these two, stratification with time series, if anybody want to add within that, like a resource on the chat, that would be very helpful. Yeah, and definitely we do not want to do some shuffling on time series. Okay, any other addition, I think, and for the newcomers to all this, this is off tangent. This is helpful, but this is off tangent because not too much off tangent, but because we are discussing like time series and all, and we may get to those kind of specific topics on later on of the chapter. So if you didn't catch something, it's fine, you know. Okay. Okay. Good. So okay, actually, still talking more about stratification. So how does he do that? So he goes to the specific one with the median income housing histogram that we've seen before, and most of the values are clustered. Most of the values are clustered between 1.5 and 6. And then here, the one that we're talking about here, it's this one. It's this one here. Okay. And if you have your notebook, you can. So it's most of the values are between 1.5 and 6, right? So what he's doing, he's gonna. So what he said. Okay, so he used this function, this Pandas cut. So this function in Pandas, what it does, this was a new function to me that I haven't seen, but it's a nice one. So what it does, it pretty much separates them into bins. So for example, here you say, okay, from values 0 to 1.5, it's going to be bin, the first bin, that's like the first bin with value 1. From 1.5 to 3, that will go into label 2, and so forth. So for example, lastly, anything above 6 will go into the 5th bin here, or label, which has label 5. And that's what we see here. So that's what we see here. So label 5 includes, for instance, all the values that were above 6. Above 6 from which column? Above 6 from when we go to our data set from the median income column, okay? So this is how he changed that histogram that we saw. This is how he changed this histogram. So he changed this specific histogram to look like this. A good question here is what's the right number of strata, right? So for example, here he used 5. Is 5 the right number? Do we want to use more? Do we want to choose? Anybody want to maybe add something to that about the right number of strata to be used?
Yeah, that was the same question I had. That's why I wanted to open it up for discussion. Like, is there some reason someone would favor something?
So for example, so what I was expecting, so at least what I'm expecting, you want the stratas to be about the same size, because what's the end goal? The end goal is you want to sample about the same number of samples from all the stratas, right? So for instance, though here, this one seems to have maybe less than others, right? So I was expecting to kind of see overall about the same. That's my expectation, and I believe that that's what we're trying to get to, and that decides on the number of stratas. How does that sound, guys? Anybody want to add? Yeah, and I think so. So yeah, I think 5 here is good. Let's say if we did more than 5.
So can I say something?
Yeah, please.
Generally, the principle that you talked about, which is to ensure that each of the categories has an equal representation in the test data set, I think that's a very sound principle. But one has to be careful about the. Sorry, what I meant is that representing equal amount of rows for each category in the training data set is a very sound principle. And it also makes sure that your model is well balanced. But if your training data set is well balanced, but your test data set is not, then you pay a price in terms of predictability, in the sense that your prediction scores will be less than what it could be.
But to follow with that, but if you do take care of this will take care of this from the training and from the testing as well. Why are you saying that we may have a balance for training, but we may have an imbalance for testing? Is there
because usually you split the test data set from the trained data set before you start examining the features and the imbalances.
Right. But the strategy.
And also in real life, what may happen is that you may produce a model based on the data you've been given, and then this has to now predict some new data which is going to come in some future date.
Okay, so if I can add to that to just make that clear. So if we are considering stratification, we want to do stratification before we split on the test. You know, like we don't want to split the test to you know, our data set to train and testing, and then we go to stratification. No, we want to do the stratification, so the stratification applies to both, really, to the train and test sets. And this is exactly why he has this here: stratified train set and stratified test set. You see, does that make sense?
Yeah, it makes sense. But as I said, the real life situation is that the model is prepared on one kind of data which has a certain stratification, but when it is applied in real life, comes the data with a different kind of stratification.
I think that is valid, but that is a different problem altogether. I think if you stratify or don't stratify, if your data changes from what you have trained, your domain is shifting, that is something your model can never kind of cope with, I imagine. So I think that is a very general problem about how you should be careful, but I don't think that is that much connected like with the stratification that we're talking about right now. At least that's what my take is. And still, I'm kind of confused whether, first of all, if you look at the PD cuts here that he's passing in, the values are so uniform. Now, is there some reason why you would want to make it non-uniform? Would you want to like make one bin bigger than the other bin? Is there a defect to that? Like, if going off your point, Salim, then you want to change the bin size if you want to kind of make the counts equal. Correct. Right? Because you won't have these spikes then. And I was just wondering if someone has experience to talk more about this or any discussion.
Yeah, has anybody used this before? Okay. So yeah, so here, just following up with your, so when you said confused or so maybe the slight confusion here, what's the right number of stratas to be used, right?
So I think there are two parameters, right? You can either pass the number of strata or implicitly you're passing what your bin size is.
Yes.
Right.
So you're saying yes, exactly. So
yeah.
you're saying actually either change
those numbers, right?
Or change the values. Yes, exactly. But both are valid. Yes.
So you could still have the same number of bins, but I could like make the first bin extremely large.
There's a comment in the chat, and I want to like echo what Sriram said in the chat. Right, it kind of depends on your application. So if you were like, it's a little bit more difficult with a numerical continuous variable, maybe to say where and how much you should split. But if you have maybe like age group of people, maybe you want to have unequal groups of people because you want to group teenagers together and maybe like young professionals together and maybe pensioners together. So maybe you don't want to have equal bin widths, if you know what I mean. So it really depends on the, I guess, your application, in my experience.
I like that example. Yeah, that makes so much more sense now.
I think the main thing is to avoid having bins that are so small that they have only a few examples in them.
Of course, yes.
So I think the author even mentions that. So that's what my next question was. When you define small, kind of becomes ambiguous for me. Like, is there like a rule of thumb that you go with small? Like 1,000 seems like 1/8 the size of the largest bin over here, or 1/7.
Yeah. So okay. So for example, and you see, like a lot of this comes with experiments, and that's why there is always like a reference point where you have to check how are you doing. So for example, he did it this way, and I believe this is fine how he did it. Why? Because when we go and then when we compare the results here, what we're looking at. So for example, here where we look at the overall and the stratified versus the random. So okay, and by the way, so here he oh yes, so here he split them into 5 already. what he's showing here, that if we just use random sampling versus stratified sampling, the random sampling is more off than the stratified versus the overall. So here, what we have is, what we're saying is like 35% of the instances are like label 3, 31% of the instances are label 2, and that's right. That's what we saw from here. And again, yes, your points, all of your points are still valid. What's the 1,000 versus the highest one, the 8,000? But what he's showing here is that doing stratification on these is better than just using random sampling.
Just to add quickly, in a link that I just had shared like a few minutes ago on the stratified shuffle split, inside the sklearn source code, apparently it's looking for that min size that we're speaking of is like 2. If any class, the count of values is less than 2 is what it's counting as a min value. So to answer that question on what's the minimum.
Okay, that's for the minimum value, right?
Number of.
That's the minimum, yeah, but that still doesn't answer like what's the number overall of how many, right?
Okay.
Right? Okay, but so you know, so I think it's like many other things. There isn't like one specific number of the stratas that we want to use. So I believe, for example, like here, would have everything be wrong if we used 6? I don't believe so. We can actually change this to and again, how are we going to validate this? Of course, it's at the end with our model validation. So actually, please guys, so a week from today, when we are all done with this, maybe we can just go this and just change this, and then we compare the change here with the final result of our model, how it did. And I think that would be a good, a fair comparison, maybe, right? And we'll see how much does it really matter, really, between maybe 5 bins here, or 7, or even maybe 10, and so forth. There should be a point. There should be a point where there is a difference, but there's something that we can figure out. Okay.
Yeah, I think, sorry, if I can, what
please.
Maria said seems to be the goal rather than boundary conditions that limit what you're trying to do. Because what she said is the business objective that you're after and the groups you would like to create is what should be your driving objective when you do this. And other things like too less, too big, not enough in the multiple groups are all boundary conditions, quote unquote, that you just ensure that you're not violating. But what drives you is what she said. I would put it that way when you're trying to do this.
I actually agree. That's a very good point. Thank you for that. Yes, definitely.
And also one more point will be like, when you see the graph, you see that there are highest number of entries in the in 3 and 2. That shows the the middle class people, and definitely and we have this data set capped at 5 because that's how the data set was captured. So the 1% of the top billionaires will be also in the category 5, or however, I mean, how the data was captured.
Yeah. But again, but just to follow this one, I mean, we can change those parameters to what specifies really a bin, right? Right.
Yeah, I mean, that depends on how you want to classify your strata, whether do you classify the middle class as someone who earns less than $20,000, or between $20,000 to $40,000. Depends on my use case. As Maria also said, when you classify age, you want to classify below a person below 19 as a teenager.
Okay, guys, I think this is good. There were so many good insights. The business one, to follow that's actually, that's true, not for this one, for in general. Yeah. So okay, let's keep going. And again, even if next week, if there are anything that comes up, feel free to ask a question again, or if you found something new about this, please share. Okay, now we're going. Okay, so we compared here. Okay, so that was the last thing, and he showed that using stratification is better than using random sampling. I believe there was a question somebody posted about this. But yeah, we spent quite a bit of time on test set generation. Yes, sir, we definitely did spend a good amount of time, but I think it's worth it because there were many points that were discussed. Okay, moving on. Discover and visualize the data to gain insights. Okay, so this is a lot of this, I believe, overlaps with EDA usually. So exploratory data analysis, and that's usually the first thing that we want to do with the data. So first, we put the test set aside, and you're only exploring the training set. If the training set is very large, you want to sample an exploration set to take manipulations easy and fast. Okay, so for instance, here what he does, he plots longitude and latitude, and he shows, and this kind of looks like, this is California map, right? So latitude, longitude, and then what he changed between here and here, he used this alpha to show the density of the points. So, and with that, you can see that, for example, I believe this is the Bay Area. This is the Bay Area. This is south going to LA and San Diego and so forth. So here what we're saying, and then he took it even to another level where he added not only the density, but on this one here, he added the colors represent the price. Okay. So this is a nice example of how we want to explore the data. So we start really just simple. We can just start like just plotting like a scatter plot of these two together, okay? And then we say, oh, okay, well, it looks like maybe some dense, a lot of points are centered somewhere, like clusters, like different clusters. Well, you know what? How about visualizing that, okay? And that's what we did. How about even taking it to another level? Was somebody can say something? Okay, how about taking it to another level? Adding like another feature here. So what did he add? He added the price. And then from this, it is very, very clear that there is a relation between the price of the house and the location of the house, right? You can see that definitely the Bay Area is a lot more expensive than here. Same thing here for, I believe this is LA and San Diego. So around these big cities. Okay, are very much related to the location. Exactly, that's what we talked about. Now, another very important thing that we always want to look for is the correlation between features, right? So for example, because here's the thing, you may have 10 features, you may have 20 features, but if they are all correlated, let's say, for example, I'm giving you a feature that's in meters, and maybe I'm giving you the same feature in centimeters, same feature in inches, same feature in foot, and those, they don't really serve anything, you know. They may be named differently. Let's say if we didn't have the meter unit or centimeter or inches, oh, you may think, oh, these are but really they're correlated. They're only acting as one good feature. So this is something that we always want to understand. What's the correlation between the features of our data set, you know? Again, here, for example, when we get to the deep learning part, now we're not talking, the deep learning, it's okay. Like we're getting to a level, as many features as you give it, it's fine. It figures its way, it figures out. But usually here we want, especially when we're doing kind of like these regression problems, we want to understand the correlation between the features. So for instance here, So he uses the standard correlation feature. Pearson's correlation is called Pearson's correlation coefficient. And by the way, this is only for linear correlation. We are not talking about nonlinear. So there is nonlinear correlation, which this coefficient is not, there are different coefficients, but here we're just talking about linear correlations. So you can see here, what we're doing is we're trying to find the correlation between the median house value with the other attributes, right? So we can see, you see this one does not, okay, it says that median income is the closely correlated to this, okay? So for example, let's go to our notebook. If we go to our notebook, okay, by the way, again, we did not run through this, but please go back and just copy and paste and run through this, even with the stratification. Go back and play around with it, change the values here, see what you get, and so forth. Just get comfortable with it. So here, what I would like to show for the correlation, let's go to that. Okay, we passed all this, we passed this. Okay, so we're started here. Oh, actually, this is okay. So so you see how here there is the map, and again on his notebook. That's why it's helpful to actually go over the notebook too. There are added cells that he shares on the notebooks that are not necessarily on the book. So, for example, here what he did, he downloaded an image of the California map, and he kind of overlaid that on, just use the matplotlib over the feature, the scatter plot that he did. So go over there. So for example, this is the one, right? This is the one that we're looking at. So we can see here that the median income is the most correlated with median house. But for instance, if you want to see the correlation with the total bedrooms, right? You for example, you can see that there is a high correlation between the bedrooms and total rooms in the house. The population, right, and the households, and look how all these four are really in a way correlated, but then the rest is not correlated at all, which is good. So these that signifies that we have some very different features that we can use. So that's good. So yeah, that's what we're kind of looking for when we look at our data. And talking about this Pearson's correlation coefficient. So when it's 1, that means here, for example, it's 1 because of course it's correlated with itself. And by the way, and you can look up the equation for this correlation coefficient. The Pearson's is just the covariance over the standard deviation of the two that you're doing. But we have, I believe, this function. You can, I mean, I'm sure scikit-learn have it. By the way, so for example, here when you are here and you would like to look at a function. So for example, let's say you copied a function and you're like, oh, okay, what's this function? Okay, so if you press Shift Tab, so okay, you put Shift Tab. Okay, it shows you a brief summary about it. Pretty much it shows you what's in the docstring. If you press it actually twice, it shows you the whole thing. It shows you like, okay, what's the docstring hopefully has some things on it, maybe parameters, maybe examples as well. This is what it returns. Here, for example, this one has examples and so forth. So this is just a quick way while you're working through the notebooks instead of just going and saying, oh, okay, this and that. Yeah. Okay, so and actually, since we have this, so method Pearson's, that's the one. Actually, this Kendall and Spearman, these are the two nonlinear, the two nonlinear coefficient correlation coefficients. Just to throw that out there. Okay. Okay, cool. So 1 and -1 usually means there is a strong, either a strong negative correlation or a strong positive correlation. 0, when it's around 0, there is no correlation there. Okay, so this covers that. Any questions up to this point? Okay, we are almost done with this. So you know what? Let's just, yeah, we're almost done. Whoever had to leave, that's fine. If not, we'll just wrap up maybe in 5 to 10 minutes. So that way next time we'll just start straight up from prepare the data for machine learning. Okay, let's see. Well, what's here? What's left? Okay, we talked about correlations. Great. Here, he just shows another way to check for correlations. Oh, okay. So here he uses the scatter matrix here. So it's just another way to kind of see it. The only thing here is since there are 11 numerical attributes, right? The different ones, all these attributes. It's gonna try to actually, it does, so 11 to the power 2, because it does the correlation between each one, so we can't really see that here. That's why here he selects only this. So he says, for example, you know what, I'm just only gonna select 4 attributes and I'm just gonna see the correlation between these 4 attributes. But this is just another way to visualize correlation. You can go through that. Let's see, the most promising attribute to predict the median house is the median income. So let's zoom in on that correlation. So he took this one and he zoomed in on the correlation between the median income and the median house value. Well, so what are we seeing here? Okay, it reveals a few things. There is indeed a strong correlation. Anybody maybe, we're here, anybody maybe wanna talk about this one here? So what are we looking at? What are we looking at here? The correlation is very strong. Yes, we can see correlation very strong. You can clearly see the upward trend and the points are not too dispersed. Second, the price cap that we noticed earlier is clearly visible as a horizontal line, right? And this is why, you guys remember why, because anything above, I believe this one was capped at this 500, right? And again, this is something that we talked about last time, that it was very important. So when something is capped at a specific value, we definitely want to consider that. Because, for example, we don't want to make predictions. For example, there is a house that's 600,000, right? But the data set, and this is inherent on this data set. This is just an issue that we're dealing with this data set. The house was 600,000, but on the data set, and I believe we had a long discussion about this, on the data set, it was just capped at 500. We want to be very careful about this, especially if there's something that we were trying to predict, right? We don't want to train on that. Okay, but anyways, but this plot reveals other less obvious straight lines. Okay. Okay, so you may want to try to move in the correspondence to prevent. Exactly, that's what we're talked about. Okay, so lastly, again, please, I'm just rushing through this, but please read this on your ease. If you have any questions, we'll go over them next time. And experimenting with attributes combination, we can actually do attributes combination, kind of like same how we seen earlier. You see how he got the identifier when we're looking to do the hash function. He was said, oh, okay, let's find this unique identifier, and then he used the longitude and latitude because those are unique to the specific. Same thing. So here he used 2 different attributes to derive a third one, which is very often done. Which is often done, and yeah, you just get other attributes now. And you just again measure the correlation between that specific, the median house, with all the attributes, even the new ones, right? So does he have the rooms per household here? Rooms per, yeah. So he has those added and so forth. Hey, not bad. Yes, not bad. The new bedrooms per room, okay, much okay. Correlated. this round of exploration does not have to be absolutely thorough. The point is to start off on the right foot and quickly get insights. And that's actually, yes. You know, it's nice to spend a good amount of time on EDA, especially, for example, if you're doing Kaggle competitions, you always, because it's such a, you always spend a good amount of time in EDA, but then you move forward to getting your model. And sometimes you may go back to your EDA and you may find other insights that that maybe you got through by working through them. But hopefully, even if you go back, you have already split your test set, and your test set is a side. So that way your assumptions and whatever do not affect your test set. And with that, I will ask for last question.
I'm sorry.
Yeah, please.
I think even though this says end-to-end machine learning project, I think it just assumes a lot of the model assumptions to be checked. But I think a lot of times we still have to run through like the regression model assumptions just to be sure that we actually can use regression in real life cases.
So when you say the model assumptions, what do you mean exactly by the assumptions? Like, are we talking about regression here or classification or?
Just regression, like are the errors normally distributed? Is the relationship linear or otherwise? And also the independence and stuff like that. I think he was just checking the correlation, but there's more stuff you can do.
Yeah.
Oh, okay.
Can I add something?
Yeah, please.
So here, I think what this person meant is that there are certain rules that have to be obeyed by the distributions for ordinary linear regression to be carried out. And those things haven't been tested here. So for example, if you, this diagram, exactly. If you look at this diagram here, you can see that this cloud is becoming more spread out as you increase the median income. So this indicates a problem of heteroscedasticity, in which you can draw a line of best fit, but you can see the points spreading further and further away from the line of best fit as you go in a particular direction, which means that this is an issue which needs to be taken care of sooner or later if you want dependable predictions. So there are various issues like this which come under the discipline of, when you study regression from a purely statistical point of view, there are some issues like this which need to be looked into.
Interesting. Thank you for that. Any other addition? So, and going back to your assumptions, yes. I mean, yes, we do make assumptions at the beginning. And again, we always want to be aware of all the assumptions that we did, because sometimes we may make assumptions at the beginning and we would want, and maybe later on throughout the experiment, that we go back and free those assumptions, maybe using some other things. So it's very important to keep in mind the different assumptions that we make. Any additions? I think besides rushing through this last subsection, but we covered it mainly. We covered everything pretty well. Any other questions or addition? Yeah.
Can we start maybe half an hour early next time, so that if anybody has questions on this section, they can ask you next time?
Yes. What we can do, we'll check with Joseph, since he's the one managing this, and if he's fine with that, we can.
Okay, I don't think this would work because we have a class that immediately precedes this that goes until 10.
Okay.
So yeah. So any suggestions like those? Please, yeah. Let's coordinate with Joseph, because yeah.
Post, one suggestion would be post the questions, and people will chime in on Slack as always, so that only we can again start off at the regular time, but answering the questions if something remains not answered from the post.
Yes, definitely, of course. Yes. Okay. Yes, let's do that. Well, we'll start the same as usual, same schedule, but please, yeah, if you have any questions, have them ready, and we'll discuss them before we move forward. Okay, everyone. It was great, and with that, you have a good rest of your day, and I'll see you all Wednesday. You take care.
Thanks again, Salim. Terrific.
With pleasure. Thank you, guys. Thanks, everyone.
Salim.